Привет,
Привет.
Аршак.
Привет.
Рада тебя видеть.
Здравствуйте.
Здравствуйте, Аршак.
Здравствуйте.
Да, Аршак, обрати внимание, Нина Николаевна будет слушать.
Да, здравствуйте, Нина
Ага,
Николаевна.
да.
Привет.
Здравствуйте.
Так, очень хорошо. Так, сейчас я... так,
Привет!
Здравствуйте.
здравствуйте.
Hello.
Так, окей. Значит, так, Даш, я тебе
Передаешь, да, я в курсе.
валяю рекорд, во-первых, и давай я на всякий случай тебя передам, да?
Ну, передавай, хорошо.
Ага, все сделал. Вот. Хорошо, значит, теперь так, Аршак, на всяк случай попробуйте, вы же экран будете выдавать, да?
Да. Мгм.
Да, вот.
Сейчас попробую.
Попробуйте это сделать.
Так,
Ага.
Сейчас
Ну,
сейчас только.
всё видно, значит, вы тогда подготовьте.
Так, наверное, лучше.
Да,
Да,
Да?
да,
отлично,
да, все
отлично,
прекрасно.
отлично.
Мгм.
Да.
Хорошо,
Мгм.
значит, тогда сидим, ждем.
Мгм.
Окей, давайте начинать. Значит, мы продолжаем заседание нашего семинара имени Смирнова. И сегодня у нас в гостях Аршак Петросян из Соединенных Штатов. Значит, пожалуйста, Аршак.
Спасибо большое. Спасибо за приглашение. Я думаю, что это прекрасная идея, что было бы намного приятнее, конечно, быть там у вас в Санкт-Петербурге, конечно, но почему бы не использовать вот эти технологические средства? И я должен на самом деле сказать, что я буду делать мой доклад на английском. Вы меня извините, но вы можете меня перебивать в любой момент и можете задавать вопросы на английском или на русском, неважно. Вот. So my talk's title is Almost Minimizers for the Thin Obstacle Problem. And this is a joint work with my student, Seokmin John. So here at Purdue University. What I'll do in my talk, I'll first start with the thin obstacle problem. So I'll tell you, in few details, so what this problem is about. Then I'll talk about the almost minimizers, and then I'll talk about the almost minimizer for the thin obstacle problem, and then we'll go to the technical part of the talk. So I'll talk about the monotonicity formulas, and also how we apply those to the analysis of the so-called free boundary in the problem. Okay, so the thin obstacle problem. So suppose that we are given a certain open set in Rn, so call it D, and then suppose we have a certain smooth hypersurface, so which we'll call the thin space, so we'll call it M here. And so this M divides D into two parts, which we denote by D minus and D plus. Now I don't go into detail how this happens, so just imagine that it's how it's on this picture. And so then on this thin space M, we're given a function C, which we'll call the thin obstacle. And then we're also given a function G on the boundary of the domain D, which are going to have the meaning of the boundary values. And then we have one compatibility condition that is G is greater than C on this intersection of M and the boundary of D. And so this is how the graph of C will look like. So this is the case when C is actually constant. So and so what we do is we minimize the Dirichlet integral, so as the standard Dirichlet integral of the domain D, among all functions that equal to G on the boundary, but are restricted to stay above C on the intersection of M and D. So the minimizer looks like this. Okay, so the thin obstacle so kind of pushes from below. So on the minimizer. So otherwise there are no obstacles. This of course would be a harmonic function. So but with the obstacle, so the minimizer is going to stick at some places to the graph of the to the obstacle. And so the important distinction of this problem from the just standard Dirichlet problem, right, is that the occurrence of this coincidence set, so where the minimizer touches the obstacle, and most importantly, so is the place so where it separates from the boundary, so called free boundary. So when we are away from the thin space that is away from M, then of course there is no obstacle there. So the minimizer is going to be just harmonic. Okay. But on M, so there is so certain conditions have to be satisfied, and it turns out to be that those conditions are as follows. So they're written here. So first of all, U has to be greater than C, and also the sum of these two normal derivatives from both sides is greater or equal to 0. This essentially so the graph looks like on the picture here. So you have a roof-like shape. So the sum of the normal derivative is no negative. So exactly means that. And so the third condition so is an important one. It says that essentially it's either U is strictly greater than C, or so these two guys are greater than C, but some of these two guys, but never at the same time. So this is so-called complementarity condition. So these three conditions are known as the Signorini conditions on M. And that is why sometimes we call this problem the Signorini problem. So this is not the system, the Signorini system, but so because of the conditions that we have on M, we call this a Signorini problem. So as I said, so the main objective in this problem is to study the regularity problems of properties of the minimizer U, and also perhaps more importantly is to understand the structure and the regularity of the free boundary, that is the boundary of the points where the graph of U separates from C. Okay, so we are going to denote this by gamma U. So it's the free boundary. Okay, so now I just want to mention briefly that where this problem occurs. Now so the original of these kind of problems. They started with the original Signorini problem, that is the problem from elasticity. So imagine you have some elastic body at rest, and then on a hard surface, and so you have some contact points of that elastic body, etc. So the problem that describes that is of course a system. So it's more complicated than the one that we'll look at, but so they are related very much. So because of the same kind of unilateral condition. Okay, so that is, we impose U to be greater or equal to Psi. So there it will be the displacement of that elastic body are in one direction only. Also this kind of problems occurs and when you model, let's say, the flow of, let's say, some solution, some saline concentration through a semi-permeable membrane. There are also related problems on heat control, etc. So and all these problems can be written in the form of variational inequalities. Now, in the recent years, there have been also applications. So in financial maths and in the study of so-called American options. And the type of the problem that I'm talking about, so these are for the options that are based on the model of the asset price that may change discontinuously, that the stock prices may jump. So they're modeled not with, let's say, the Brownian motion, but with some jump processes, so like Levy processes. And so the simplified version of that would be so-called obstacle problem for the fractional Laplacian. So Laplacian to fractional power s between 0 and 1. And that problem can be written in the following way. So these three conditions, u minus phi no negative, Laplace to power s phi no negative, and this product is 0. And these three conditions really similar to the ones that I had before for the Signorini, the complementarity conditions. And in fact, they are exactly the same conditions when one uses so-called Caffarelli-Silvestri extension. So this would correspond to the thin obstacle problem that I'm looking at will correspond to s equal to 1/2. So the half Laplacian is exactly the normal derivative. So after you do an extension to a half space from let's say Rn minus 1, well, so you have a slightly different dimension, but so if you extend your space by 1 dimension, so you can write the half Laplacian as the normal derivative of the extended function. Okay, so I'm not going to go much into detail about this, so because that's a whole different story. All right, so now what I want to tell are the results, known results for the regularity of the minimizers for the thin obstacle problem, and also results about the free boundary. Now, in general, so when you look at the minimizers of the thin obstacle problem, then you notice that, so at best, the regularity can be Lipschitz because the Lipschitz corner may occur in the minimizer. And here you see on the picture, so it's an explicit solution, so that I've written in this form. So real part of this xn minus 1 plus I times xn to power 3/2. So these 3/2 will play a fundamental role, we'll see. So it's essentially the best regularity or the optimal regularity in a certain sense. But so if we look at the regularity across the thin space M, then so the best regularity possible is M. Is Lipschitz. Okay, so which is not good. So in certain sense, but what it turns out is that if you look at your solution, at your minimizer only on M, restrict yourself on N, or on either side from M, then the solution is actually better. So it's in fact, so it's C1 beta, let's say, for some beta. And this has been known for quite some time. So under different assumptions on the right hand side. So this has been proved by Caffarelli in 79, then Kinderlechner in 81, then by Nina Nikolaevna in 85. So extended to the parabolic case as well. Now and then after that, so there was some. There were no really any significant developments until 2004. So there was a paper by Athanasopoulos and Caffarelli where they established that in fact this exponent beta can be taken 1/2 in all dimensions. Now I have to tell that of course exponent 1/2 has been known for much longer, I think, and early 70s, maybe even late 60s in dimension n equal to 2. So so that's much easier to treat. So with, let's say, complex analysis tools. So but for higher dimensions, so this really has been a breakthrough in 2004, and this kind of started a series of papers. In fact, there was another significant development in 2008 by now Thanasopoulos, Caffarelli, and Salsa. So where they used, in fact, a different method to achieve the same results. But so this new method that they used allowed much much deeper study of the problem, and essentially whatever I'm going to talk about is going to be based on the method of this second paper. So this Thanasopoulos, Caffarelli, and Salsa. So they extended this the optimal regularity, the C1 so to the flat case, but possibly non-zero obstacles. And then so this later was extended to non-flat AMs. So then also to the fractional obstacle problem I mentioned earlier, also to the parabolic case, and so on. There are many results in this direction. So obviously I won't be able to mention all of them. So that's the regularity. But now let's see what we can say about the free boundary. Okay, and to state the results about the free boundary, so I'm going to look at the simplest case possible. That is when the thin space M is just the hypersurface, xn equal to 0, and the thin obstacle psi is 0. So, and domain D is symmetric with respect to M, and also we have the symmetry condition that it's even the function U is even symmetric in xn variable. Now, in this case, so there is a very important quantity that is used to classify the points on the free boundary. This is so-called the Almgren's frequency formula. So when we have x0 on the thin space M, and we'll look at this quantity nr at x0, so defined as follows. So we have this directly integral over the ball times r divided by the integral of u squared on the boundary of the ball. So this quantity, again called Almgren's frequency function. So this function is monotone in R. So as long as the ball is contained in the domain. So this was proved in this paper I mentioned by Thanasopoulos, Caffarelli, and Salsa in 2008. But this formula is proven much earlier by Almgren in his study of the multi-valued harmonic functions. So in this so-called big regularity paper, so of course it also played the important role in that paper. Interestingly enough, so the thin obstacle problem and this Q-valued harmonic function, multi-valued harmonic functions are related. In fact, so one can view the solutions of the thin obstacle problem as two-valued harmonic functions in a certain sense. Okay, so that's why it's not surprising that this formula works. And so because of the monotonicity, of course, the limit this limit exists of the frequency function at a point as we let r go to 0, so n at 0 plus, and we call it a frequency at a point. Now, another way to characterize this frequency at a point is the following. So essentially, it can be found by also looking at the this normalized L2 norm of U or L2 average of U on a ball of radius R, on the sphere here, the radius of R. And so taking this limit, essentially what it means is that so U is going to grow like R to power kappa. Okay, so and one can go back and forth between these two quantities. In fact, so because the absolute value of U or plus, positive negative parts of U, in fact, are subharmonic functions. So anyhow, so the meaning of this kappa here is that your u grows like the power of kappa at that point. Okay, and so yet another characterization of this frequency at a point is that one can look at so-called Almgren blowups, so Almgren rescalings first. So here this quantity that we have here, this UA x0r, so it's essentially rescaling, so normalized rescaling of U. And so if we look at the limits of those rescalings, so those are called the blowups. And we are going to use different kind of rescalings as we'll see. So this one we indicate with A, with superscript A here. And the limits of those we call Almgren blowups. So the characterization of this frequency in terms of the Almgren blowups is that it turns out that the Almgren's blowups are going to be homogeneous of degree kappa. So that is, if we look at this blowup at lambda times x, then lambda to power kappa comes out from U. All right. So now, so why is this frequency so important? Is because so we can we use this, of course, to classify the points on the free boundary, and we can split the free boundary gamma into the union of gamma kappas. Okay, so that is gamma kappa are the part of the boundary where kappa x0 is fixed. And so the important question is, so what are those values of kappas? So are they arbitrary or not? So well, it turns out that first of all, no, they are not arbitrary at all. So the kappas have to be greater or equal to 3/2. And this is the same 3/2 that occurs in this optimal regularity C1 1/2, right? So C3/2, if you like. And also importantly, so what they showed, the Athanasopoulos, Kafrel, and Salsa, is that so kappa can be either 3/2 or greater or equal to 2. So there is this gap between 3/2 and 2. Now, this of course doesn't answer at all on what are the all possible values of kappa. So in fact, if you go to dimension n equal to 2, so this has been known again since 70s, early 70s, or even late 60s, is that so the only possible values for kappa, in fact, are very discrete. So it's 3/2, then 2, 7/2, 4, and etc. So 2m minus 1/2. And 2 m's for m being integer. And this has been known again for n equal to 2, and so there are no results of this kind for high dimensions. Maybe until a couple of years ago, then Focardi and Spadaro proved that up to a set of Hausdorff dimension n minus 3. So all this is true. So that is the only possibility for the kappas is the ones that are listed above for dimension n equal to 2. Now I have to mention that the free boundary itself, gamma u, has at best so dimension n minus 2, because so the thin space in n minus 1 dimensional, so and free boundary is yet 1 dimensional less, so it's n minus 2. So n minus 3 is kind of the next dimension, next small dimension. So, so similar result is also true for the multi-valued harmonic functions, in fact. So, and again,
excuse me, can we discuss some question at this point to understand further?
Yeah, absolutely, yes.
Yeah, it's about, am I understood correctly that x0 is a point on the free boundary here?
Yes,
x0.
yeah. Mm-hmm.
Yes. So if we have the case n equals 2, and we have this thin obstacle, then what is free boundary? Is it?
It's a point, yeah, it's a point.
The single point collection of
they are going to be isolated points.
What we mean by this?
They are going to be isolated
points.
Yes, yes.
Mm-hmm.
Yeah, so it's not.
If we apply formally this limit and these quantities to the point which is on this thin obstacle, but not on the obstacle, which is in the part where the equation holds. What will be
Yes.
this quantity? It will be 0 or what?
No, it may not be monotone.
Limit.
So it may not be monotone. Okay, so let me tell you this. Yes. So if we go back to the Almgren's frequency formula, yes. So what will happen is the following. So if the point is on the thin space but not on the free boundary, this quantity is still monotone. This is true. So what I mentioned that kappa is greater or equal to 3/2 will not hold, but it will be greater or equal to 1, and 1 because of the Lipschitz regularity. So this will pick up the essentially. So this quantity will pick up the regularity of the solution. So for x0 away from the free boundary, so it will be greater or equal to 1. But so if you are on the free boundary, then it will be greater. Then it will be so this result so greater or equal to 3/2, and also this. Now in dimension n equal to 2. So you would still, so even if you are away from the free boundary, so you're still going to have discrete values, but those will include now 1 and also the other half integers like 2.5, 3, 3.5, etc. Well, actually I don't know about 3, so maybe I should be careful about that. So, but again, the values will be discrete. So, but this restriction will no longer hold. So it will be greater or equal to 1. Okay. Now, if you go. Yes, all right. Okay, so now, so what we know about the possible gamma kappas for different values of kappa is the following. So we know what's happening with in the case when kappa is 3/2, and this is the so this gamma 3/2, that is the gamma with the smallest possible frequency 3/2. So this is called the regular set. So for historical reasons, let's say. So, and it turns out that x0 is in this gamma 3/2. It's equivalent to saying that any Almgren blow-up is going to be this real part of x prime times e prime plus ixn to 3/2. So this is the same function or the rotation of the same function I showed earlier. So that has the regularity 3/2. So essentially, we can classify all the blow-ups up to a rotation in the thin space. So because of this, so one can prove a regularity theorem. I'll mention it on the next slide. And next, so also we know what's happening in the case when kappa equals to 2m, in integer. So this union of this gamma to m, so we denote by sigma u and call the singular set for the reason is that x0 is in sigma u if and only if the so-called coincidence set where u equals to 0 has density 0 in the thin space. Okay, so this quantity here that's written is essentially the density of the set where u equals to 0. And so this density is 0. And it's also equivalent to saying that every blow-up, Almgren blow-up at that point is a polynomial. Okay, so these three things are equivalent. And again, because we know what these blow-ups are, so one can also study the structure of this set sigma u. And so these are the theorems that one can prove. So the first theorem is on the regularity of gamma 3/2. So it turns out that it's locally a real analytic manifold. So no surprises here. So the C1 gamma regularity was proved by this paper by Athanasopoulos, Caffarelli, and Salsa. And next there were two results on the C infinity and the real analyticity of this gamma 3/2. So both almost simultaneously in 2015, in fact 2014. So these are publication dates. So by De Silva and Savin for C infinity regularity, and by real analyticity by the Koch, myself, and Shi. But they use completely different methods. So this one is so-called the boundary Harnack principle, higher order boundary Harnack principles, and this one by using the partial Legendre-Odograph transforms. Now, for the singular set sigma u, so what is currently known is that, so the sigma u is contained in a countable union of so-called C1 log manifolds. And in fact, so there is a stratification type of result. So one can, in fact, write the sigma as a union of subset sigma d, and those will be contained in countable many manifolds of dimensions d from 0 to n minus 2. Now, I'm going to talk about this at the end of the talk, so hopefully. So I'll give more details maybe on this. And so the C1 regularity was approved by Garofalo and myself in 2009. And the C1 log is a recent result by Colombo, Spolora, and Velichko with so-called log epiperimetric inequalities. I'll also talk about that hopefully. So the C1 log means that these are C1 manifolds with logarithmic models of continuity. So in fact, it's a power of log. So we'll see. This comes up naturally from the method that is used there. Okay, so these are the overview of the obstacle problem. And now let me move to the another ingredient, the so-called almost minimizers. So now in 1983, Ancelotti considered so-called almost minimizers or omega minimizers for the Dirichlet integral, which are as follows. So now instead of asking that U is the minimizer for the Dirichlet integral, we ask that on every ball, BR x0, so centered at x0 at radius R, so we have this inequality satisfied that the Dirichlet integral over this ball of the function U is less than or equal to then 1 plus little number here, omega R, times the integral of any competitor function with the same boundary values. Now, in the case when omega is 0, so we'd get a true minimizer, but so in general, so what the aim is that to have omega R being just some non-decreasing function with omega 0 plus equal to 0. So that is as R goes to 0, this omega R disappears. And so we call this, so Ancelotti calls this kind of objects as almost minimizers or omega minimizers. Now later on, we're going to take very specific omegas like R to power alpha between 0 and 2, because the results are best in this case. And the motivations for starting this almost minimizers, some of them are as follows. So you can view those as some kind of perturbations of minimizers, and I'll make this more precise. I know this is very vague, but I'll make this more precise on the next slide. So also it turns out that certain minimizers, let's say with constraints. So for instance, if you take the minimizers with volume constraint, or even solutions of the obstacle problem, so they turned out to be almost minimizers in the sense of Ancelotti. And also, you know, this kind of notion it's true. So it was considered in this context of this minimizers in the calculus of variation, but in 1983. But in fact, this had appeared earlier, maybe by a few years. So in geometric measure theory, so Almgren and Bombieri, for instance. So look at the almost minimizing currents. So these are related objects. Now,
excuse me, can
yes.
I ask again?
Yes, absolutely.
Can we consider this conception close to the case when we simply replace obstacle condition by a penalty term with, and then consider minimizer of this penalized problem? Will it satisfy such type relation? So in a sense, this omega can be treated like something which generated by a penalty.
Well, maybe. So maybe yes, maybe one has to be careful. So if you have a penalty term with the dependence on epsilon, so probably yes. Now, my true motivation actually looking at this almost minimizer was a little bit different. So in fact, so I wanted to look at the minimizers with variable coefficients, which are also can be kind of viewed as the perturbations from the constant coefficient case. Yeah, so one has to, so essentially, let me tell you, so one has to be careful with yeah, so if you do it with a penalty term, possibly, but depends again, so what kind of penalty term it is. So
I'm not saying that it is one-to-one, but it seems somehow related.
Could be, yes, could be. Now, so let's make another observation before I proceed, is that so the type of the almost minimizers that we look at and are so-called multiplicative almost minimizers. So the error term here appears as a factor. Now there is also a related notion of almost minimizers, so-called additive almost minimizers, where the error terms will be just additive terms, not multiplicative like here. And so possibly, if one has the penalty term, so one may get additive type of almost minimizer instead of multiplicative. So there is going to be an important distinction, at least for us, in this problem. So I want to mention that so sometimes in the literature, so when it's considered the additive the almost minimizers in certain cases are treated as the additive ones rather than the multiplicative ones. Okay, so all right, now so let me just proceed and tell so what kind of results Ancelotti could prove, and I'll give some details in the proof as well, because it's rather simple to understand in this case. But before, so the main difficulty in the study of this almost minimizers is they don't satisfy any PDE. So that's the problem. Okay, so essentially what you have to do is resort to comparison with carefully chosen competitors. Now, in the case of just the Dirichlet integral, so there is an ultimate competitor, the so-called harmonic replacement. So that is, we take a ball, BR x0, and replace the function u in that ball with a harmonic function, with the same boundary value, so called h. So again, we call this h a harmonic replacement for the obvious reason. And so this almost minimizing property is then equivalent to asking just this one, right? So that the gradient of u squared is less than 1 plus omega r of the integral of the minimizer of this. So that is the harmonic function, gradient of h squared. And so because of the harmonicity of h, so the same inequality can be rewritten now as follows. So we'll have that this integral gradient of u minus h squared is less than this omega r times the integral of h squared. And so this is what I meant, that one can view this as a perturbation of the minimizers. Okay. So in fact, this inequality will play a fundamental role. So in most of the regularity properties one can prove for u. And so in his paper in 83, so Ancelotti proved that, so if you have an almost minimizer with omega r equal to r to the alpha, then u is in fact is C1 alpha half. Okay. So I want to give the details of this proof as I mentioned, and so the proof essentially so is by energy methods only. Obviously, there's no PDE, and so he starts with the almost Lipschitz regularity of the solutions, and he proves that almost Lipschitz regularity by Morris space estimates as follows. So if we start with the harmonic replacement h of u in a ball of radius r, BR x0, then this harmonic replacement satisfies this kind of estimate on these two concentric balls, B rho and BR. Now, if you look at this inequality, this is nothing but the submean value property for the gradient of H squared. So if H is harmonic, then gradient of H squared is subharmonic. So, and what's written here is the submean value property. Now, if we use that, that argument, so with the perturbation argument I showed on the previous slide, so one can show that for the almost minimizer U now, you have the perturbed version of the above inequality. And once you have this inequality, then from here it's a standard, so the standard lemma, so which will tell you that now the gradient of U squared, so will be less than constant times rho to any power less than n. So here we have power n. So here you have to take any power less than n. So I've written this as 2 sigma minus 2 with sigma less than 1. And the reason I've written it this way, because then there is this Morey embedding theorem, of course, which says that, so this is the Morey space, right? So Morey space estimate. So, and this tells that the U is in C0 sigma. So it's Holder continuous for any sigma between 0 and 1. So this is what we say almost Lipschitz. Okay, so now after this, Ancelotti proved the C1 alpha half regularity with Campanato space estimates, and so one starts with the appropriate inequality for harmonic functions. So again, so H is the harmonic replacement, and so this inequality for harmonic functions is also relatively straightforward to prove. So you can decompose into the sum of polynomials, etc. So it's very straightforward to prove this inequality for harmonic functions. And then you proceed to prove the perturbed version of this. And the perturbed version of this is now as follows, as I've written here. So these braces, triangular braces, are the average values over the balls of radius rho here. And once you have this kind of inequality, then it implies the Campanato space estimate like this. See, so the L2 oscillation, let's say, is less than constant rho n plus 2. And from here, one can conclude that the gradient is C0 alpha half, or U is in C1 alpha half. Okay, so this is how this works. Okay, how the perturbations can be used to prove the regularity of the almost minimizers. All right. Now let me move to almost minimizers for the thin obstacle problem. And I'm going to look at the simplest possible case, that is when M is flat, Psi is 0, and omega r equal to r to the alpha. So in this case, so what we do, so again, we look at all functions that are restricted to stay above Psi 0 in this case. So what we ask that the gradient of U squared to be less than or equal to 1 plus this r to the alpha, this omega r, times the gradient of V squared for any competitor V, which again has to be constrained to stay above Psi, okay, or 0 in this case. So it's not a true minimizer again, but it's a minimizer up to some multiplicative error. Again, in this problem, so we are interested in the local properties of U, regularity of U, and those of their free boundary. So free boundary is again defined as the boundary of the set where U is 0 or where U is positive on the thin space. So this gamma of U lives in this line here in M. Okay. Now, so there have been other, free boundary problems considered from the point of view of almost minimizers. This has been done for so-called Alt-Caffarelli Friedman type free boundary problems by David and Thoreau, and also David Engelstein and Thoreau. So they studied up to the regularity of the free boundary. And also this has been studied by different method by De Silva and Savin, both in the so-called thick case and in the thin case. So there's a thin counterpart of this problem similar to the one that I'm looking at. But I have to say that all these free boundary problems are rather different because the growth rates of the minimizers from the free boundary points are fixed in these problems. And in our case, so you can have this range of kappas. So these are quite different. And again, so the main difficulty is that so we don't have the PDE, and also there is no explicit way to write the free boundary condition. So not only the PDE, but also there is no way to write that free boundary condition. And also in general, so we cannot do the harmonic replacements, because when you do the harmonic replacement, so your function can go below the obstacle. So we cannot do that. So instead, so we use the Signorini replacements. So that is, we take the ball of radius r and solve the Signorini problem with the same boundary values. So by Signorini problem, again, we understand the thin obstacle problem. And also, it turns out that there is another kind of replacement that that is very useful, the so-called kappa homogeneous replacement. That is, in the case when x0 is 0, so we replace the function u with inside the ball with the homogeneous function of degree kappa. That is, we take the values from the boundary and extend it homogeneously inside. Okay. All right. So next, so I want to describe the results that we know for regularity results for almost minimizers. And so I'm going to assume that the domain D is B1, and also that my function is symmetric. So the first result we proved with my student Seong-Bin John is that U is almost Lipschitz. Now this is relatively simple. In fact, the same proof as for the almost minimizers work. So one establishes this version of the Morey space estimate. So remember, this implied the Morey space estimate. And this time, this comes from the perturbed version for the Signorini problem, for solutions of the Signorini problem. In fact, so if you have a solution of the Signorini problem, H, you still have this inequality because the gradient of H squared is still subharmonic. So, and that's why you still have the same argument. So this works relatively, easily. So the next result we proved, so it's in fact U is C1 beta on either side of the minimizer, and so this was much harder actually, because in fact it is not C1 beta, so it's C1 beta on either side. Okay, so but the idea of the proof is the following. So instead of looking at the gradient of U to prove the Holder regularity, in fact one has to look at the even extension of the gradient of U. So we take the gradient of U from let's say 1/2 ball and extend it in an even way to another half of the ball. So call this gradient with hat. And so then what we proved is that this the Campanato space type estimate now holds for this gradient U hat. And the way to do it is to of course first prove this kind of thing for the minimizers for the solutions of the Signorini problem, and even that was not really easy. So one has to carefully do odd and even reflections. So depending, so it's kind of reminiscent of the fact that one can look at the solutions of the thin obstacle problem as two-valued harmonic functions. So in fact you have two branches in a sense to work with. So and when you do it carefully, you end up with this inequality, and then from here, so you get that this U hat, the gradient U hat is C beta, which exactly implies the C1 beta regularity on both sides. Now I have to mention though is that so this is not a new proof of C1 beta regularity even for minimizers, because we do use the C1 beta regularity for minimizers. Okay, we couldn't we couldn't do it without. So this is not not a new proof, but rather a perturbation argument to prove that the C1 beta regularity for the minimizers implies that one for the almost minimizers. Okay, so this is the regularity, and now so I want to move to the free boundary part, and so here the technicalities start. And so we need some technical tools, the so-called monotonicity formulas. Now, so I've mentioned already, so the Almgren's frequency function. So this played a fundamental role in the case of minimizers. And so, of course, we want to have something like this for the almost minimizers. Okay. Now this turns out to be a bit tricky. So, but eventually we got it. So, but we got it indirectly, and I'll explain how. So in 2009, so in the paper with Garofalo, so we introduced this one parametric family of Weiss-type monotonicity formulas. So those go back to work of Weiss, Georg Weiss, in the case of classical obstacle problem. And this is how they look. So it's sometimes those are called boundary adjusted energy functional. So we have here the normalized Dirichlet integral minus a boundary integral. So and it turns out that these quantities are all monotone. So when we take x0 on a free boundary, in fact, it doesn't have to be free boundary point, but it has to be on the thin space. So similar to the n. So it turns out that all these guys are monotone for any kappa positive. Okay, and if you look carefully at n and this w0 kappas, then they are composed of the same quantities. So here we have the integral of the gradient h squared over the ball, and here we have the integral of h squared over the boundary. So here we have the ratio, here we have the difference. And it turns out that monotonicity of n is equivalent to monotonicity of this family of omegas. So this was observed again. So already in 2009. So in this paper by Garofalo and myself. But so we just mentioned it, but we didn't really find it, any real application of it. But we did find the application of it in this paper. So for the almost minimizer. Now the proof of the monotonicity of the devices for functional is based on direct computation. So one can differentiate it and use the PDE, the underlying PDE, and then also the free boundary conditions. And one can derive a very nice formula for the derivative of this W functional. So in fact, this is this nice neat formula. And it also tells you the case of equality. So when this H is constant, this W is constant, then your H will have to be homogeneous of degree kappa. So now, so if we don't have a PDE or the free boundary condition, so how do we even hope to prove anything like this? Well, so we proved the perturbed version of this, but it's so the proof of this theorem is kind of interesting. So, but first, how does the perturbed version look like? So there is the new terms that appear here. This exponential function with the coefficient a kappa r to the alpha. And also instead of kappa in the Weiss's formula, we have this term 1 minus beta r to the alpha. This is of course related to to this omega r equal to r to the alpha. Now here's the important thing: this b can be taken as a constant depending on kappa 0 for a range of kappas between 0 and kappa 0. This a kappa cannot, so there is some dependency there, but so this is not really that important. So the important thing is that this b here is independent of kappa. Okay, so that's the important thing here. And also, so this thing will be monotone for a range of r's between 0 and r0, also depending on kappa 0 only, not kappa. So about the proof of this. So when we looked at the original proof of Weiss, so in the case of obstacle problem, it turned out to be that in fact it doesn't use at all any equations, any PDEs. It turns out that in fact what he does, the only thing he does is one single comparison with the homogeneous function. So which we call the harmonic replacement. Remember, so we had this competitor, the the homogeneous replacement, sorry, not harmonic, homogeneous replacement. So turns out that if you use just one comparison with the cohomogeneous replacement, then so you are going to get this kind of inequality that I've written on the next slide, so on this next line. And if you do algebraic manipulations, no PDs, no derivatives, nothing, absolutely nothing involved. So you can write it in this form. It's one has to see the computation to believe this, but it is really true. So from here to there, it's just an algebra. Okay, so there is no PDs or anything involved. Okay, and this is remarkably similar to the differentiation formula in the Weiss case. So there we had the equality, and there were these error terms, but inequality is good enough for us. Okay, so so that's how we get the Weiss's monotonicity formula just with that single comparison. And and now we can state a version of Almgren's formula, and it's as follows. So we fix a certain kappa 0 large, but greater or equal to 2 at least. So but can be as large as we want, can be 10 million, whatever, doesn't matter. So then we'll look at the truncated version of n. So we call this n hat. So it's a minimum of n divided to 1 minus b r alpha. So this is the same b r alpha that was also in the Weiss's formula, and a kappa 0. So we really have to truncate this with kappa 0. So and then we get this range of r's. So this is monotone in this interval. And the proof by using Weiss's formula is as follows. So if we look at this truncated n, so nr over 1 minus br0 less than kappa 0, so this inequality can be rewritten. So if we recall the definition of n, exactly in this form. But up to a positive factor, this is precisely the same as saying w kappa r is less than 0. And why? So when this w kappa is less than 0, then you now can use the monotonicity of w kappas, and then you can write that w kappa s is less than w kappa r for s less than r. And then this is equivalent to ns minus bs alpha is less than kappa. So from here, we get that for any s less than r. That is precisely the monotonicity. Okay? So we give this indirect proof of the monotonicity of this truncated Almgren's formula. So from the family of Weiss formulas. Okay, so now starts the most technical part. So how much time do I have?
I think up to 10-15 minutes.
Okay, that would be enough. Thank you. So now, how do we use this monotonicity formulas? So now, because we have these different kinds, so we have this Almgren's formula and Weiss formulas, so they work best for different kind of rescalings and the corresponding blowups. So I've already mentioned the Almgren rescalings. So that is, we look at u x0 plus rx and normalize it in this way. So this normalization kind of gives you the integral over the boundary of the unit ball equal to 1. And this plays very well with the Almgren's frequency function. Again, if we look at the blowups of this rescalings, so-called Almgren blowups, then because of the condition is omega r going to 0, so we'll get that the blowups are in fact minimizers of the thin obstacle problem. And because so we know what are the frequencies for the minimizers, we then have the same inequality as we had before. So kx0 is 3/2 or greater or equal to 2. So this is the reminiscent of the result that we know from the for the minimizers. Okay. Now another kind of rescalings that are very useful are so-called kappa homogeneous rescalings. So in the case x0 equal to 0, so they simply look like u r x over r to power kappa. Now this work well for this unperturbed version of the Weiss formula. So the w kappa is 0. So the 0 meaning this unperturbed version. But they don't work really well for the perturbed version of the Weiss formula that we have. So to take account for this this perturbation, so we'll look at almost kappa homogeneous rescalings. So which are slightly modified version. That is, we divide not by r to the kappa, but by a function phi r, which is e to the power cr alpha times r to the kappa. The reason we look at this kind of almost homogeneous rescalings is because of this differentiation formula. That so if you differentiate this rescaling with respect to r, then you get this quantity here, kappa times 1 minus b r to the alpha, which is the same one as in the Weiss monotonicity formula. Okay, so by looking at this almost homogeneous rescalings, you want to take advantage of the Weiss's formula. All right, now so the main question is that, all right, so how do we take the advantage of Weiss's monotonicity formula? Okay, and so this is I call controlling the rescalings. So this is a bit technical, but hopefully not too much. So by using this differentiation formula here, so this on this last line here, so one can write how the L2 norm of this almost homogeneous rescalings behave. So one can estimate it in this way. All right. So with the Weiss monotonicity formula here, because we had the same quantity there as in the Weiss's formula, and from here by integrating, we can see how the L2 norm of this rescalings change. So there is going to be this integral here log, and then there is going to be the square root of this difference of omega kappas and r and s. So this is one type of estimate we can do. So the second type is that one can also estimate the how close the two rescalings to each other on the unit sphere. And because they are they're almost homogeneous, so this would also mean how they are close in general. So and it turns out that again this w kappa quantity appears in this estimate, but there is also this logarithmic term. Okay, so this logarithmic term is really annoying, and it's really bad. So one wants to get rid of this logarithmic term. But unfortunately, so if you don't have any further information, so let's say only you have a free boundary point and the frequency is greater or equal to kappa at that point. So the best you can do is this kind of estimate on the growth rate of u. So there's this logarithmic term times a good term. So this is what you want to have. You don't want to have a logarithm. And then, unfortunately, from this inequality, you cannot really say that the difference of use is, the rescalings are close to each other. But, so if you know some additional information on w kappas, then you can do it. And here are these two cases. So one case is when omega kappa at the w kappa.
Arshak,
Yes. Yes.
What is you say that it you wish to prove that it goes to 0 as what?
Okay, as R and S go to 0.
Okay.
Yeah.
Okay.
R and S go to 0. Yes. Sorry. Yes. Yeah. So that is as we approach to the blow up. So essentially, this would show that the blow up is unique. So, but unfortunately, without additional information, we cannot do that. So, and how we can, so what additional information is useful in this case? So if we know that the W cup is less than a certain constant times R to certain delta, so for some positive delta, then, so one can use a dyadic argument so that is apply this inequalities above here with R and S, powers of 2. Then once you do it, so you can get rid of the log term. And in fact, you can also get this nice estimate on the rotation of the rescaling. So we get that this difference is less than R to power delta half. So essentially, we get a very nice, even a Holder modulus of continuity in certain sense, right? So there's one case, and the second case. So even in a weaker case, right? So when you have a power of logarithm 1 over logarithm of 1 over R to some power of delta here, delta greater than 1, then even in this case, you can do this exponential dyadic argument. That is, you take R and S being e to the power 2 to the minus 2 to the n's. So, and apply it in this case. So then you, again, can get rid of the logarithms. So you get this nice growth bound here. And here, the models of the continuity or this difference is going to be power of a logarithm. Okay, so very well, but can we really prove these two inequalities? So can we really prove that omega kappa is less than constant R to the delta or logarithm to a certain power? And turns out, yes, in 2 cases. So in the case when kappa is 3/2, there is this very interesting result. This is called Epiperimetric Inequality. So this goes back to minimal surfaces, in fact. So, and the result is as follows. If we have a certain 3/2 homogeneous function, no negative, on the thin space, so it's admissible for the competitor for the thin obstacle problem. And we solve the thin obstacle or seniority problem with this boundary values at W. Then it turns out that the Weiss's functional, this W 0.3/2 of H, is geometrically better 1 minus eta times the energy of W, the Weiss's energy of W. And this eta is a coefficient depending on n. Okay, so this was first proved by Garofalo, Smith, Vega, Garcia, and myself, and Focardi and Spadaro in 2016. But I want to also mention this work by Colombo, Spolar, and Velichko in 2017. They gave a very specific value for this eta. Okay, and their proof is much better than ours. So it's much more explicit. So so because of this very nice improvement, so what one can, if one goes back to the proof of the Weiss's formula I mentioned before, and uses this fact, in fact, one can prove something better. So one can prove that this kind of inequality holds, and this does imply that W is less than constant times R to the delta. So we're done in this case. So what this implies, so I'll just mention this quickly, is that so the gamma 3/2 is a C1 gamma graph, or locally, or C1 gamma manifold. So the same kind of proof. And so I want to skip this and go to the singular case. Now it also turns out that in the case when kappa equals to 2m, so there's a version of the epiperimetric inequality called log epiperimetric inequality. And is as follows. So again, the assumptions are the same. So we have a kappa homogeneous function, but so with some additional assumptions here on the normalization assumptions. And then, so if you solve for the seniority problem with the same boundary values omega, then we have this kind of improvement on the Weiss's energy. So there is no constant here, but the power of W0 of W. But gamma is very specific, n minus 2 over n. And so this result is due to Columbus, Polar, and Velichkov, 2017. And so when we use this one, so in our estimates, turns out, so it's technically long, so one can do bootstrapping arguments. So if one has a growth estimates with the power of logarithm certain power sigma, so we start with sigma equal to 1. And then by using this epiperimetric inequality, one can prove this kind of bound on W, and then reduce this sigma to sigma minus 2 and minus 2 by a little bit, but by a fixed amount. So you do this iteratively until this becomes negative, okay? And once this becomes negative, so you arrive at a clean estimate on the growth of U squared, and also with this kind of estimate on WK, so with the exponent here greater than 1, n over n minus 2 greater than 1. And this allows then to control the rescalings, prove the uniqueness of blowups, and so on, and complete the study of the free boundaries, the free boundary points. So I don't know, I guess probably I don't have any time left, but so let me just mention here that the theorem again is that so if we use this fact that we can control the blowups in a nice way, so with this logarithmic power between two different rescalings, then one can show that so the singular set is contained in a union of C1 log manifolds. In fact, this log, the modulus of continuity is going to be exactly the log to power minus n over n minus 2. Okay, so it's exactly the same as you get in that from the epiperimetric inequality. Okay, so I guess that's all that I wanted to tell today. So, and thank you very much, and stay safe.
Okay, thank you, Arshak. Questions or comments, please? So it was very nice talk. Even I have got something.
Okay, thank you.
Yeah, no, really clear. Mm-hmm.
Arshak, one question.
Yes.
And what about parabolic part? Is it work in progress, or
So okay, yes. So yeah, let me tell you this. Yes. So first of all, there's a question: what are the almost minimizers in the parabolic case? And that's a very good question. So, and that's a very good question. But there is an answer to that. Yes, there is a way to look at the parabolic problems as some sort of minimizers, and there is a way, yes, to look at the corresponding almost minimizers. So my student recently, so Sungmin John, recently found that. So we started working on that, but there are no results yet. So, but and there are, in fact. So the thing that gives us the hope is that there is an epiperimetric inequality in the parabolic case, even though it also relates to the minimizers. So, but there is so one has to do it carefully. So one does the change of variables in the way that transforms the heat equation to more like the Ornstein-Uhlenbeck type of equation with the time. Time derivative. So, but yes, there is. So there is. So hopefully one can do something. Yeah.
Okay. Thank you.
Okay. Thank you again. Значит, что касается дальнейших заседаний, то пока я ничего сказать конкретного не могу. Следите за объявлениями, вот, и старайтесь не болеть. Вот. Все, спасибо. Спасибо.
Спасибо большое.
Мгм. Мгм.
Good. Я останавливаю.
Да.